All right, so we've got these amino acids, various amino acids that we have. What if you have a mixture of amino acids and you want to separate them, right? Very applicable situation. Well, we can separate them relatively easily. So this is known as a process of electrophoresis, at least one way to separate the amino acids. Maybe you've done this type of experiment in your biology or biochem class. If you haven't, you probably will eventually. It can also be used to separate DNA. So oftentimes, you do like a cheek swab, and then you extract your DNA, and then you do electrophoresis on it. We did that in CHEM107 when I adjuncted here. You can also use separate to RNA and proteins as well. It doesn't have to be just amino acids. It can be proteins as well. We're just going to take a look at amino acids to, kind of understand what we're doing here. So what you start off with is either some kind of gel, or sometimes it's just paper and it's just dipped into an electrolyte. Electrolytes are just compounds that are ionic, and it allows charge to flow, so it becomes conductive. Right, so conductive gel. And then we're basically going to hook this up to what is essentially a battery, right? Depends how fancy your setup is. And then as soon as you do that, right, you're going to charge this conductive gel. One end is going to be positive, one end is going to be negative. And it depends where your amino acid, which side is it's going to go on, depends on its charge. And its charge depends on how protonated or deprotonated it is, which we can summarize through the pi. So for example, if your pH is less than your pi, right, that means that your compound is essentially in an acidic solution. So everything's going to be protonated, which means everything's going to have H+. So it's going to be more positively charged. If your pH is greater than your pi, that means that you're in a relatively basic conditions, and you're going to deprotonate things, which means you're removing H+, so you're becoming more negative, right? So things with large, so just compare the pH to the pi, and then you can have different pHs of gel. Usually they're around room temperature. And then don't forget that opposites attract. So for example, if you have a relatively positive amino acid, it's going to go towards the negative side. And then if you have a relatively negative amino acid, it's going to go towards the positive side. And so we can separate them based on their PIs. There's also other factors that come into play, such as size. The bigger it is, the slower it's going to go to one side. So there are other factors in there, but charge is the major one. And so then you separate your amino acids. Unfortunately, amino acids are not visible with the human eye. They're colorless compounds, so you can't see them. And so what you need to do at the end is what's called stain. So we need to stain them. In this case, we're going to use an anhydride. If you don't have to know this reaction, so I'm just going to copy it out of the book. You have your amino acid, which obviously has nitrogen attached to it. And then you add some ninhydrin, and it undergoes a reaction where this nitrogen then gets placed in between essentially two ninhydrin molecules. And then this is a purple colored compound, so that way you can see it with the human eye or with some kind of instrumentation, right? And the reason that it's colored is you can see we have a highly conjugated system. So anytime you have a highly conjugated system, it's going to appear as some kind of color. Another kind of cool thing about this reaction is you totally destroy your amino acid. This R carboxylic acid and all of these groups, even these hydrogens, they actually just all end up as byproducts, right? Water, carbon dioxide, and an aldehyde. The only part of your molecule that stays on the stain is the nitrogen, which is kind of a cool idea.